And in switching to this topic, and an interest now, we're almost stepping away from geogrids if they're primarily used as the material of choice in reinforcement of walls and slopes. And we're moving to a world of geotextile filters, on occasion geonets as a preferential drainage medium, or on occasion the very low cross-plane conductivity of a geomembrane. Then our interest switched to hydraulic properties, and I enjoy thinking and trying to create a logical framework for taking and defending decisions in filter design. It's a subject that has intrigued me over the years. To tell you the truth, ever since BC Hydro asked me, going back a long time now, in the 1990s, to advise on rehabilitation of a dam, and the question was, might geosynthetics work? And I went into it with an open mind, thinking, might they or might they not? And discovered that there was a paucity of good data, materials, properties, as well as good test methods to allow any designer to make an informed choice with confidence. And that triggered some industry university sponsored research, both with the manufacturers of geotextiles and also I ended up writing the specification documents for the project, and being on site for placement. And subsequently to that, and this has been a little bit of a privilege, I've been more recently heavily involved in looking at the performance of non-geosynthetics, granular filters and drains in a number of dams, both in Canada and in the US, and indeed in South America and Europe. Probably now about 10 dams. And so it's been fascinating to look at geotechnical practice with granular filters and drains, and geotechnical practice with geotextile filters. And so my learning objectives in moving to material properties to inform filter and drainage applications with geosynthetics, I'm going to be trying to reflect on how we would do it if we didn't have a geosynthetic, in order again to increase your ability to make informed decisions, and to do so with confidence. So those are my learning objectives for this, I'm going to call it, second half of the course. And that takes us to the material properties. I'm going to focus primarily on the hydraulic, but it behooves me just to acknowledge on the way through, and let's turn this here. It behooves me on the way through to acknowledge that we need to have a sufficiently strong material. So let's deal with this in one slide and tuck it away. The strength is not going to account for things like creep, which we were addressing in the reinforced soil design. The strength is going to be very much from index tests for strength. And some years ago, there were 4, but the burst strength turned out to be a rather unreliable. It was kind of grandparented in from previous work. And we now look at grab, tear, and puncture strength. And over time, the nature of the ASTM index tests for puncture have been changed and improved upon. So we end up with a number of ASTM tests. Let's tuck them out of the way and we're done. The grab strength, 4632. Tear strength, 4523. And the puncture strength, now with a slightly thicker rod, and that's 6241. And you know what? You could go to manufacturers' data sheets and just pick those off. And in fact, as we acknowledged, I think it was back when we were dealing with the resource access roads. Just bear with me, see manufacturers. Technical data sheets. And the manufacturers will actually go through and they may even categorize by AASHTO, American Association of State Highway and Transportation Officials. They may even categorize them as a class 1 or a class 2 material. So we're done. There's the strength. And I wanted to tuck that away. Maybe let's look at this as class 1, class 2, class 3. And so that's, it's really a categorization, not a classification, but they get labeled as class 1, class 2, or class 3 with AASHTO. Okay. And we want, one of the things that we want the geotextile to be is strong enough in a filtration and drainage application. So there's that world of strength. Done. Okay. The next thing, and now we get into the classic world of filter design. Arguably, if it was a granular filter, we want the material to be strong. We don't want it to crush. We don't want to be placing a granular filter where the material is subject to, where the soil itself, the sand, for example, is insufficiently strong because of its mineralogy or because of its grain shape, or that it's susceptible to crushing, for example. So that might be our mirror in filter design. But really, if we think of filter design, it's all about soil retention, adequate soil retention, and permeability, adequate permeability. So we're interested in design criteria for filter design. Design criterion number 1 is adequate strength of our filter medium, the geotextile. And our second criterion is adequate soil retention. And our third criterion is adequate permeability. Number 2, soil retention. Number 3, adequate permeability. It's true for geotextiles. It's true for granular filters. 1, 2, 3. You know what I'm going to do? I'm going to link the strength and say, to some extent, mass per unit area is in the background controlling the strength. It is to a certain extent. So I'm going to grandfather that in as just a convenience, and arguably because I want to try and put a line down here, and I'm going to say that the UV resistance, if we place and bury within an adequate period of time a material that is treated at the time of manufacture to have adequate UV resistance, for which there is also ASTM then from a point of view of durability, I'm going to bundle all of that in there. And that's going to allow me to park performance-oriented testing rather than index testing over here. So let's stick with the index tests first, and now be as opposed to versus performance tests. And ask ourselves, gee, if we were designing a granular filter, what kind of index tests would we do? And we might want to know something about the grain size distribution of the granular filter. Because the grain size distribution of the granular filter is controlling the pore size distribution, right? And the distinction, so perhaps let's do it, let me take a piece of paper here. If I'm looking at the granular filter, right? If I'm looking at the granular filter, I'm just looking to see if I've got anything that can help me here. I'll sketch it. Can you imagine with the granular filter, we're sizing the grains of the granular filter. Let me put the base soil here. I'm just doing this somewhat schematically. We size the grains of the filter, let's give them a big D, relative to the grain size distribution of the base soil, in essence to control the pore size openings or the pore size constrictions. Our use in granular filter design of D is actually a surrogate for the openings. Right? The grain size is a surrogate for the opening size when it comes to soil retention. Okay. And typically we might use, for example, D15 of the filter. And we might match D15 of the filter because we believe that the lower percentage size from the distribution of the grains in the filter will give us an empirical connection to the opening sizes, and then we may match that to D85 of the soil. In fact, we may even look at ratios of D15, D85, and that's where Terzaghi started in the world of filter design for certain base soils. Okay, I need to maybe put in here diameter D85 of the base soil. And subsequently to that, granular filter design has started to classify the base soil into certain categories. A nominal go-to design guide, chapter 26, design manual. We'll touch base on this as we get into the design side, but we're matching this as a surrogate. And for a geotextile filter, be it a non-woven geotextile, and this is my symbolic representation of the non-woven geotextile. Okay, it has a bunch of opening sizes, right? We can see that if I hold it up to the light, right? There's the. Do you see that? Do you see the way the you know, they've got more open areas. The opening sizes must be a little larger there. And let me go over to here, and I get a little bit of a clump about here, and the opening size must be a little smaller there. Okay, so that's the world of a non-woven geotextile. Non-woven, or there's the world of the woven geotextile. And the weaves can get quite intricate. Let me find, I don't know if it, yeah, the weaves can get quite intricate, but you see, it's very much a regular series of opening sizes there, right? I can hold it up to the light again and we see that, right? It's like a tennis racket, a mini tennis racket. And by and large, all of the opening sizes are the same. So, and we can measure. We've got an interest in this opening size, and the manufacturers will report that. We don't need a surrogate for the opening size. We actually measure the opening size. And we might give that opening size, being very clever people, if D is for diameter, O is for opening size. And we might be looking at amongst the coarsest end of the opening size. So often reported as 0.95, sometimes as 0.90, etc., etc. But we want to match not a D15 to a D85, we want to match an opening size, 0.95 to D85. So this opening size is of keen interest to us. Informed by that, the opening size is measured by ASTM, and I have apparent, and then I put in brackets, or filtration. And I learned that in the last short while, the filtration opening size, which is actually a Canadian General Standard Board, that test has been discontinued as a standard. It may come back again, but it's currently discontinued. So let's just restrict ourselves to apparent opening size. Let's put that label here, 0.95, the apparent opening size. Manufacturers may occasionally be reporting it, I guess, as AOS. And so we want to get the value of that apparent opening size, or AOS. And were I to illustrate the distinction there, I'd say that the non-woven geotextiles, which I had captured in green, if you remember, the non-woven geotextile, it has a broad range of opening sizes. Okay. View the non-woven geotextile almost as the equivalent of a broadly graded soil, broadly graded grain size. The non-woven geotextile is a broadly graded opening size. In contrast, the wovens tend to be more single-sized, and their openings tend to typically be larger. So we'll go in and we'll put the woven as a range for different products. And it's been captured here, but let's go in at 95. And say that 95 or 0.95 would be a characteristic opening size of the particle. And that is obtained by the manufacturers either by dry sieving or by wet sieving, or even hydrodynamic wet sieving, where instead of just trying to, I'll call it, seep particles through the geotextile, you can actually dynamically raise and lower it in water. And I would have spoken about that dynamic raising and lowering, but I'm going to strike this out because that FOS test is no longer holding true. So we can go to the page and speak to getting an opening size, either the AOS, which is the apparent opening size from the ASTM standard test method, and in fact other standards also work off the same basis. for example, I think British standard, and there may be, I don't carry it from the top of my head, but a number of countries have a dry sieving method. And here, for example, reporting 090 or 098 for different woven and non-woven geotextiles. Notice the woven geotextiles having slightly larger opening sizes. The units are microns, so about 0.2, 0.3 of a millimeter. The wet sieving is not giving you the same exact opening size, just because there's a little bit of different energy going through there. And so we end up with an empirical design approach, a little bit like Tertsagi's empirical design approach, matching D15, typically by dry sieving, to D85, typically from dry sieving. And it could be D85 of less than the number 4 sieve. The empiricism can be stacked on empiricism. And likewise here, we'll be looking for empirical rules between the apparent opening size. And it may or may not declare that the empirical rules are based on dry sieving or wet sieving. And that'll depend a little bit about the country where any database has been developed. And this is going to be our, we'll do things primarily now on an AOS-based approach to design. Now that speaks to, we go back to this page just to make sure we know where we are in the big picture. Index tests, we did the strength, well, almost acknowledged in passing. Then from a soil retention point of view, we'll be matching apparent opening size to grain size or base soil information. And then the third one is permeability. And I could choose to dive straight in to this page. And I could choose to do that because permittivity is the named ASTM term, the permittivity or cross-plane permeability. I could jump in right there and that would be done. But I've got this additional page, and I wanted to speak to this additional page to influence the way you think about permeability, and thus to inform a slightly richer appreciation for what we know about soils, as well as what we know or are about to learn about geotextiles. Okay. Now I took this figure from Taylor's book, 1948, fantastic book on soil mechanics. Taylor was a contemporary of Tertsagi's. I don't think they saw eye to eye, but to tell you the truth, I don't think Tertsagi saw eye to eye with a number of people. And maybe that's along the school of you can't make an omelet without breaking eggs. But Taylor wrote a wonderful book. Grab a secondhand copy, cheap as chips, and it's full of very, very interesting information dating back to the origins of soil mechanics. And one of his observations in the relation between hydraulic gradient and velocity is there is a zone where the relation is linear, and there's a zone as we get to higher hydraulic gradients where the linear relation breaks down. Anyone want to offer me a way of describing the nature of the flow regime when it's linear versus a way of describing the flow regime when it's non-linear? Can I throw that open, please? Does anyone want to throw a couple of terms that I might be able to incorporate into this distinction here? What's so magical about my flow regime that I have a linear relation between hydraulic gradient and velocity? Any takers? Or at 11:42 a.m. in Vancouver, are you you're just cruising to the end of this lecture, and please, we're on autopilot here. No takers? Going once, going twice?
Is it if I could take a guess?
Yes, please do, Alex.
Laminar flow versus like a turbulent flow?
Yes, indeed. We're making a distinction here between a flow regime that is laminar and a flow regime that is turbulent, or we might make a distinction, Alex, between semi-turbulent as opposed to fully turbulent. So I'm going to qualify it just a little bit further by saying semi-turbulent. And thank you, Alex, for popping in there with that. So Taylor observed that, and you know what? Darcy's law is good for laminar flow. Darcy's law is not good for semi-turbulent flow, and this gets lost in modern textbooks. It tends to, you'd think the whole world was laminar flow, and you'd think the whole world was Darcyan flow, and you'd think every soil, irrespective of its grain size, exhibits laminar flow and thus can be described by Darcy's empirical law, and it's not true. Okay. And that becomes important when you start to interpret advanced test data, for example, such as we're doing with some of our dam engineering work. Laminar flow, V is proportional to I. Semi-turbulent flow, V is not proportional to I, not linearly proportional to I. Okay, and that's from Taylor, 1948. And there's a wonderful series of data, and I've got one point that I'd like to make and close on in this lecture, and we can pick it up again next week. It's kind of saddling between lecture periods and lecture subject. So here's an interesting set of data. I want to see if I've got the book here. I think I've mentioned this to you before. Bear with me, bear with me. No, I think the book must be at home. It's from Cedergren. And he compiled these data. Very interesting data. Data on permeability versus, we'll talk about effective diameter in a second, but look, data from soil, sands and gravels, and data on pipe flow. Okay, oops. Data on pipes and channels. Okay, the data on the soils lie here. The data on the pipes lie here. Okay. And if we look, here's the coefficient of permeability. Now it's a log-log plot, so we'll bear that in mind. But here's the key point I wanted to get for you, is that the effective diameter of the flow channels, so the effective diameter for the flow channels in the soil is D10/5. That's how that's been calculated. Okay. And then we see that the relation between permeability and the effective diameter indicates that K, this line here would be for K proportional to D squared. So this is for the soils. We'll hold for the moment on the little curvature that happens up here. Let's observe that for the soils, right? We have Darcy's law, V proportional to I, and there are empirical relations between permeability and, for example, D10, Hazen's empirical rule, for example, or a much richer one, Kazeni-Karman's empirical rule. And both Hazen, I don't remember the year for Hazen, but it's way up in the early 1900s, and Kazeni-Karman, Kazeni was a contemporary of Tertsagi's Kazeni-Karman equation. They both have K proportional to D squared. Okay, and that's true. Although look what happens. What's happening about here? Let's carry this line up. Okay, let's carry this line up here. That relation appears to break down. The linear relation appears to break down. And if we take a close look at it, and I think it's worth doing, because it's going to inform the net. It's going to inform. Ooh, what's it going to inform? It's going to inform. It's going to come back in again. Oops! It's going to come back in again next week when we also look at what's happening in this figure. But let me just highlight a point here to cross-reference next week at about 0.01. So at approximately D10 over 5 of 0.01, or D10, and let's keep the approximately equal to 0.05 of an inch, or let's turn that into post-Renaissance units, or 1.25 millimeters. Something happens, and this proportionality to D squared breaks down. Okay. When we get into the pipe flow, we're dealing more with Reynolds numbers and things like that. Okay, but I want to look at the soils, and we see that there, and it's because we are moving from a laminar to semi-turbulent flow. In fact, you know what? If I had been really clever, I would have aligned this figure over top, because I'm going to say I would have done this. That's unfortunate. It would have been super elegant, but anyway, that's this transition. That the soils are becoming sufficiently coarse that the linear relation is no longer holding true. Okay. Now, the way in which we measure or obtain a value of cross-plane permeability for a geotextile, you know, I think I'm going to pick that up next week. But let me take a couple of moments here to synthesize on the subject of filters, what we've covered with the material properties, and then where we're going to go, and try to capture that with a closing comment on the emerging points of note. Okay, and I'll do that. I'll move to close this. That in this material properties for filter and drainage, we want to be looking at pore size characteristics, hydraulic conductivity relations, and to some extent durability. It's going to be more for the waste containment facilities. We're looking at durability. That if I provide myself a little bit of a framework for it, 3 criteria by which we will select a geotextile filter. One is it's got to be strong enough, primarily to survive construction, to tell you the truth. with respect to categories, done. That's all we want to know about that. Our main focus moving forward today and into next week is on the opening size, because that's going to help us with filter design for soil retention, and the permittivity or cross-plane permeability. We want the opening sizes of the geotextile to be sufficiently tight that they provide for base soil retention, but we want the opening sizes of the geotextile also to be relatively open so that we have adequate, and let's call it unimpeded, drainage across the geotextile. Same holds true for granular filters. By the way, soil retention and permeability design criteria. To inform our appreciation of the flow regimes, and this will be either the flow regime in soil and across a geotextile filter, or to inform the flow regime in something that's coarser. I'm going to give a little bit of a kind of a more gravel-like. Maybe the flow regime here is no longer laminar. It might be semi-turbulent. That might be true for the geonet. It might also be true for gravels. And so, being mindful of where we're headed with this, we want to acknowledge the rich legacy of appreciating whether the flow regime is indeed laminar or semi-turbulent, dating back to Taylor in the 1940s, who in his textbook was capturing knowledge that was coming out of testing labs, and Kazeni's work was very influential in that domain. And we see that expressed as we move through coarser and coarser particles. We're getting into coarse sands here, we'll discover, and then as we head out into pipe flow. And we have empirical relations that support what we're seeing there. And thus, our desire is to get this permittivity of the geotextile, that is the cross-plane permeability, the cross-plane permeability in the geotextile. And for that, we're going to take the geotextile, put it in a test device. Right, oops, let me just move this here. It's front and center. Let's bring this in a little bit closer. There we go. We're going to put the test specimen, which is the geotextile, in a rigid wall permeameter. And then we're going to conduct a constant head flow test, just like we would do to get the permeability of a soil. We put the soil in a rigid wall permeameter. We've got to be a little clever about getting it fully saturated and so on. And then we can carry out a constant head or a falling head permeability test. We do a constant head permeability test on the geotextile specimen. It's just going to be down in here. And we're going to flow water from a constant head controlled here and out through a constant head controlled here and measure the flow rate. We'll speak about that upcoming. And that's what I'm going to distinguish as cross-plane flow. So let's put the cross-plane is in this direction. And we'll also acknowledge, and this is what I want to build the framework of laminar and semi-turbulent flow, we could look at the flow inside or within the plane of a geonet. There's the geonet, there it is. And we're looking at flow that's going along the plane of the geonet. And so that would be in-plane flow. And our test specimen, we'll put in a transmissivity test device. Done this in the past. In fact, we even built some here many, many years ago. There's our test specimen. And now we're going to flow water in the plane of the test specimen from a constant head on the inflow to a constant head on the outflow, just like the constant head on the inflow here and the constant head on the outflow here. So we're going to flow water. It's going to be a little harder to. I want to stick with the in-plane capacity. I'll do it here. That's the base plate, but it's flowing within the. It's flowing within the specimen. Okay. And when we get to something as open and porous as a geonet, it behaves like an open and porous gravel, and it's non-Darcian flow. And so that's where we're going to be headed to finish this material next week, is this appreciation for Darcian versus non-Darcian flow in geosynthetics and Darcian versus non-Darcian flow in soils. And thus the strength, together with the opening size, together with the hydraulic conductivity, will allow us to go in and design in an informed way with material properties for filter and drainage. So at that point, bear with me while I